Okay, so today we're going to talk about this concept of total survey error. So when I started at Statistics Canada back in the late 1900s, I don't remember them talking about a total survey error. So what would happen is the methodologists, the math side people would talk about sampling errors, and the let's say the project managers would worry more about non-sampling errors. Non-sampling errors being mistakes that can be made at any point in the survey process. It doesn't matter what, to be honest. Everything that's an error falls under non-sampling error. Okay. So in this presentation, what we're going to go through is we're going to see what is total survey error. So what are these various problems? Why it's important, how we report it, and how we're going to use it for analysis. So all of these things are quite important throughout the entire idea of what our jobs are at our various statistical bureaus. Let me just move forward here. So for those of you that are following along on the GSBPM, so we're always, I think everything I do is probably going to fall on 2.5, which is designing the process analysis. 5.7 is sort of calculating the aggregates, interpreting and explaining the outputs, and then it's going to produce and disseminate the product. Okay, so measuring error. So error has an impact on the quality of the results being produced. Reporting error allows users to judge the quality of your data and be wary of research results that don't share their error and methods. So I'm going to talk about this one in a second. And then sampling errors are going to help researchers understand the usability of your data for the research. Now, what's important here is this idea of reporting error. And so there's an interesting story about Statistics Canada that comes from the 1970s. And back in the 1970s, the Canadian government almost disbanded Statistics Canada. I don't think I'm sort of overstepping our reputation by saying that Statistics Canada is well respected in the world. We're considered to be sort of on the cutting edge of a lot of methodological practices for collecting data. And, you know, we take a lot of pride in the work we do, and the people that work here are very proud to work for Statistics Canada. But in the 1970s, Statistics Canada used to hide, like a lot of people tend to do, is we would try to hide our errors. We would make mistakes, we try to hide from them. And it turned out, like, I mean, this is very bad, right? When you're producing official statistics, if your users can't trust the statistics you're producing, they're not worth anything. So if you, if a country produces labor force statistics saying that unemployment rate is 9%, and they have simply just produced this number and they haven't done any research to do it, no one's going to believe that that answer is 9%. They're going to say, this country has not done any work, you know, this answer can't be right. In statistics, in official statistics, your reputation is everything. If you don't have your reputation, no one's going to believe what you're doing. And so at Statistics Canada now, what we do is we jump out in front and we say, okay, here's an error. And so whenever we find errors, we report them. We report them relatively as quick as we can, hopefully within a day. But this is what we do when we report our errors. First, we report what was the error. So a recent error that we had with our last census, for example, was, and this one's really unfortunate in Canada, they overrepresented the number of English-speaking Anglophones, like English first language people in small Quebec being our French province, towns. And this was actually a little bit politically charged because there's language issues in Canada. And it was sort of interesting or it was concerning that we did this. And so when this error was spotted, the first thing we did is, okay, this is what the error is. This is the source of the error. This is why we made the mistake. This is the remedy that we're going to do to fix it. And this is the date that the new numbers will come out. And when the chief statistician or whoever needs to stand up in front of the cameras and says, and they say those four things, all of a sudden all the controversy is gone, because it's very hard for the media to sort of pick on you when you admit the error, you admit how it happened, you tell them how you're going to fix it, and you tell them the follow-up day. It's not a very interesting headline. Statistics Canada makes mistake, new data will be out tomorrow, right? they will do it. Sometimes it's a bigger issue. So we had an issue with labor force a few years ago where it was problematic that, you know, these things happen, but it's worse when you try to hide it. When you try to hide your errors, that's when if someone spots it, it's going to be really bad, because hiding your errors, it just, Statistics Canada sort of made it their mantra that this isn't something we're going to do. Whenever we find mistakes, we're going to quickly acknowledge them, and we're going to sort of promote the path forward, how we're going to fix this problem. So for us, measuring error and reporting error is very, very important. All right, so when I say the word error, this sort of bothers me. So non-sampling error can occur in all aspects of the survey other than sampling. So non-sampling error is any kind of error that exists. Okay, so an error happens, it's non-sampling error. On the sampling side, I sort of loathe the fact that these are called errors, because it's not really an error. We do this intentionally, and it's part of the design. So whenever we do a survey, we can never be certain of the result of the survey because we haven't done a census. And I think this is really important for people to acknowledge that if we are doing, the example I like to use in my classroom is, I tell people, I'm going to do a survey of the classroom, and I'm going to say, okay, tell me how many coins, the value of all the coins you have in your pockets or your purse, or your wallet, whatever, on you that day, right? And if I do this and I ask everyone in the class, I will have the exact, and assuming the methodology is correct and no one lies to me, I will know the exact amount of money that the entire classroom has in coins that day. If I do a sample, and even do a sample with excluding only one person from the class, I can't be certain of my answer because I just have no way of knowing how much that last person has. I assume, based on the statistics that we do, that it's probably close to the average. So if on average everyone's had, I don't know, $2 and change in their pocket, it would be, and I have, say, 30 people in my classroom, it's going to be very shocking to me if the last person has $80. So this is sort of how sampling error works, is that we anticipate that there's going to be this lack of knowledge. So I loathe the fact that we call this errors. And in fact, if I'm ever become the chief statistician of the world, I would change sampling error to something else, something like sampling, there's some other word. I haven't spent a lot of time on this because I don't think I'm ever going to be voted chief statistician of the world. But if I do become chief statistician of the world, one thing I will fight very hard for is to remove the word sampling error and call it something more like, I think sampling uncertainty is the word I really like. There's an uncertainty that goes along with the fact that we're drawing a sample. And this is what I much prefer to have in place rather than errors. But you know, this is just me trying to be chief statistician of the world. Okay, the first part of this presentation, we're already sort of 20 minutes in. The first part is on non-sampling errors. So mistakes that can make, what they are, how we can fix them, how we can sort of control for them. So non-sampling errors come from all sources. We see a bunch here. They can happen at the planning phase. They can happen at the interview phase. They can happen at the processing phase. There's all sorts of different ways we can make mistakes. We're all human. We all have good days. We all have bad days. These things can happen. Sometimes it's systematically done, which can be problematic. So for example, coverage errors, there may be something that we're doing wrong with the way that we have been looking at our population. Slippage rates has to do with non-response of longitudinal surveys. And that has nothing to do with the people that are working in the statistical office. Interviewer effect, I think I talk about this on the next couple slides. So I'll let that one go. Now, for reporting of non-sampling error, it allows the users to understand what may have affected the outcome. So if you have an error, a big error that's happened, it's good to report it so they can say, okay, they're telling me that they've made this thing has happened. And I can now sort of absorb that as a user of the data and say, okay, I'm going to either, that's a small error, it's not going to bother me, or that's a big enough error that I'm really going to be concerned about the data they're producing. An example I like to use for this sometimes is I'll often hear on the morning radio show, when it used to be on my drive into work, the hosts would often read the newspaper before going on air, and then they talk about things that they read in the newspapers. And this one host frequently be like, oh, I just read about a survey that was done. And then she would talk about the survey results. And it always sort of stressed me that this was now sort of word of mouth. She may get the numbers exactly right that were published in the newspaper that came from the survey, but what she's done is she's eliminated the source by saying, I read a survey or the results of a survey. And quite often what these were from were things like magazines asking their readers to write in, or to fill out something on the internet, or it was very specialized groups. So if I were to do a survey of all, let's say, people that like to do recreational sport fishing, if I then don't report that that is my population of sport fisher people, that it's going to be, my results are going to become very strange to the general population when they look at how much people are spending on fishing as a general, for example, or how much vacation time is spent fishing. Unless I tell them, well, this was only a survey of people who fish, this won't make sense. So this is another example of non-sampling error. All right, so coverage errors, frame defects. So this is where we're leaving units out, or units that could have been included, or we've included units that shouldn't have been. So we've accidentally left businesses in, for example. These things are easy to have happen, especially with frames. The biggest one I think we have to worry about, especially on the business side, is like when businesses go out of business, it's quite often, the cleanup process for our business frames, it's very specific. A business will have to not respond for a certain number of cycles before we might entertain the idea that they no longer exist. So it's very possible that if we're just doing a sample, that we're going to sample businesses that no longer exist, or we might, new businesses that have just come into existence, we might not have them yet because of the fact that the administrative files from whichever government department just haven't made it to us yet. With measurement error, so we may have more poor questionnaire design. So we may have respondents giving incorrect answers. And this may simply be the respondent not understanding what the question is. An example of this that I've seen, not at Statistics Canada or of any of our partner bureaus, but I saw this on a more of a business one, like business in the sense of a private polling business. They would alternate between personal questions and household questions, like one after the other. And so you'd lose track very quickly to know, was I answering on behalf of myself or was I answering on behalf of my family? So it became very tricky and it became very easy to give incorrect answers. If you have poor training of interviewers, this can be a real problem. So it could be that the interviewers are accidentally biasing the answers, and it's very easy to have this happen. The way this can happen is you might give a leading statement to them by accident. So for example, in fact, example is what I'm going to use. You may say something, they may ask something like, have you, let's say it's a consumption survey, have you shopped at, what stores have you shopped at this week? And we leave it like that. That's the way the question's been designed. And that's the way it's going to be. So have you shopped at any, what stores have you shopped at this week? If the respondent doesn't understand the question, the interviewer might say, what stores have you shopped at this week? As an example, and they start listing off a few stores that are local to that community, the respondent will almost always repeat back the exact same things they just heard. Or we've sometimes do like physical fitness surveys. If you say, you know, what measures have you taken to maintain good health? For example, proper diet, exercise, good sleep. People will often say, oh yes, all three of those, even if they're lying to us and to themselves. So it biases these answers towards getting these same answers that the interviewers keep giving as examples, which is really bad for us. Non-response errors, so subpopulation was a higher non-response, and maybe we have poor follow-up. We talked about that last week when we talked about weighting and reweighting, so we've talked about this already. We could have processing errors. So sometimes what we'll do is for example, we'll do age ranges. We'll ask the respondent, how old are you in years? And then we might try to code that into age ranges, such as, you know, 0 to 17, 18 to 34, 35 to whatever. And if the person coding it codes it wrong, then it's going to make a mistake with what these variables say. And then edit, we talked about this during edit and imputation a couple of weeks ago. So it's very possible to have edit errors as well. All right, this is sort of the meat of the presentation. This is where it's sort of on the technical methodology side, this is where it's going to get good. We're now going to leave non-sampling error behind. So we can either now say we've done a magical survey where nothing's gone wrong. I don't even think it's worth talking about an example like that. We should more say, let's talk about an example where we did a survey to the best of our ability. We tracked all the little errors that we made. We've made some sort of report to acknowledge it. And now we're looking at the analysis of the data. So this is where we're at now. So now we're at the sampling error, or as I like to call it, totally erroneously, sampling, what did I just call it? I had it in the tip of my tongue. Oh, well. So sampling error occurs when we sample from a population, right? So some of the ways that we measure this, sampling uncertainty, that's what I always want to call it. Some of the common measures of this sampling uncertainty is sampling variance, standard error, confidence intervals, and coefficient of variation. And I'm going to go through all 4 of these in the next sort of 25, 30 minutes. Now, why is it important to report sampling error? This one's much more important for the researchers. So this will give them, depending on which one they're looking at, which one of these measures, it will tell them the possible range of the answers. And this will allow for comparability with other data sources. So for example, if Statistics Canada publishes that GDP changed by 1% last month, and the Bank of Canada would use our data, and some external business, Google maybe, said they're changed by 1.1 or 0.8. Giving these range of errors would say, okay, well, yeah, okay. StatsCan said 1%, Google said 1.1. It's actually in the margin of error, so they're both saying the same thing because they're both talking about ranges. And it also, if you're doing like more advanced statistical testing, you'll actually need some of these values to be able to conduct the test to see if things are significantly different from one another or not. All right. So here is sort of a dartboard picture that we use. And so there's 4 possibilities here. And so you've got imprecise and biased, which is this type A. They're not really called type A, it's just A, B, C, D. And then B is this imprecise and unbiased, and C is precise and biased, and D is precise and unbiased. Now, I always like to make the joke internally at StatsCan, and I'm going to make it to you, that 100% of all of StatsCan surveys fall under category D, which is precise and unbiased, because we're just that good. In honest truth, that's not the case. And in some cases, you don't even want that, which sounds a bit weird, but sometimes budget or time or whatever it is doesn't allow for it to be that precise. Sometimes an imprecise answer is as good as we need it. Now, I'm going to open this up to the chat and see if anyone wants to answer this. Which one of these 4 is the scariest? So because I'm using a word like scariest, I can probably say there's no wrong answer. Does anybody want to hazard a guess in the chat, either to me privately or to everyone? Which one of these is the scariest? Which one of these would give me nightmares if I was working on a survey? All right, so someone has sent it directly to me. They've said the answer is C. As far as I'm concerned, C is correct. It's the correctest one. The problem with C is the precision of our data makes it seem like it's doing the right thing. I'm getting the same result over and over and over again. So I become very comfortable. Oh, I'm always getting the same result. My survey is working. But in this case, it's biased. It's not giving us the right answers. So this is gravely concerning to me. When I first started working in Statistics Canada, I had a full head of hair. Now I am bald. It is situation C that has sort of caused this to happen. Why is my slide not advancing? Why is my slide not advancing? So when we talk about accuracy, unbiasedness is necessary and sufficient condition for accuracy. So unbiasedness and accuracy are effectively the same thing. So in this case, when people talk about how accurate a result is, they're talking about condition B and D. If you want to say how accurate is A or C, you have to say they're not accurate in the sense of they don't give you the correct answer if you repeat it over time. B and D are both accurate, One is very accurate, which is D, and the other one is not very accurate. So going from not accurate at all to accurate means that you produce an unbiased result. And then you have to use adjectives to sort of describe it. All right, so let's take a look at variance, standard deviation, and standard error. So suppose we're tasked with doing a study. I use in my example to find the average age at Statistics Canada. You can pick your office. To be able to do it correctly, though, your office has to have at least 11 people in it. Otherwise, my example is doing a census. So everyone taking this course, I asked them to go around Statistics Canada. Statistics Canada has 3 main buildings. So one building is 26 stories tall. The middle one is 3 stories tall. And the other one is, I think Jean Talon is 13, 15 stories. Yeah. So anyways, there's about 5,000 people who work at Statistics Canada. So I tell them, I want you to go out. We don't actually do this, but I tell them it's a thought exercise. Go out. We're going to randomly select 10 people, and you're going to calculate their average age. And we're going to do this over and over and over again until we start to get a result. And we're going to sort of use this example to, I'm going to talk about variance and all these things using this example. So if I want to take a look at the age range of Statistics Canada employees, again, this is usually a discussion I have with my class, but I would say the youngest employees at Statistics Canada, there are probably 18-year-olds. We hire summer students, we hire co-op students. So 18-year-olds, there's definitely 18-year-olds at Statistics Canada. The upper age range, Canada doesn't have mandatory retirement laws anymore. So people can be sort of any age. People can be any age. They can work till any age at Statistics Canada. Our 2 chief statisticians ago was Ivan Falagi. He was chief statistician for, I believe, 40 years. And at least up until the pandemic, he still maintained like a chief statistician emeritus office at Statistics Canada and would come in at least once a week and would be happy just to talk statistics with any staff that worked here that had any questions they might have for them. So we would have, we had staff that were much older. So anyways, this is the range. So 18 to 70 is the range. And if we walk around and we start talking to people, we see that if you end up talking to all 5,000 people, you end up with almost a solid bar of potential ages. Every age is covered by 5,000 people when we're talking about 18 to 70. So these are the potential individual answers. But when I tell you to go out and sample 10 of them, when you come back, it's going to be much more difficult for you to get certain answers. So for example, if there's exactly 10 18-year-olds at Statistics Canada, it's nearly impossible for you to actually go and sample at random all 10 18-year-olds in one sample of 10 people out of 5,000. Like we talk about Lotto 649, that would be Lotto 10 5,000. It'd effectively be impossible. If a student came back, or if any staff came back to me with that answer, I would tell them that they had cheated on the survey. And what they did was they found a table in the cafeteria of students playing cards at lunch, asked them how old they each were, and they were all 18, right? So this isn't a good sample. What's going to happen is it's going to be somewhere much more in the middle. You're going to find a few old people, you're going to find a few younger people, but when you calculate the average of these 10, they're going to sort of narrow down. And the example I like to use for Statistics Canada, I don't know the actual answer, but to make my life easy, I always say that the average age is 40. So as we continue to conduct this survey, as more and more people come back with the results, I start to see values in this range. And you can get outliers. It is possible to select at random, like the poor man from the Australian Let's Make a Deal that I didn't get to show you. He drew a horrible sample and he selected all of the most expensive cases to eliminate. It's possible here to get a very high or very low age. And it's actually a good thing, before I go on, it's actually a good thing to get very high and very low estimates. What that does is it tells you that there's variability in the data. So for example, if I came back and I always got roughly the same answer, let's say the number always came back as being 39, 40, or 41, I would start to get the idea in my head that maybe everyone in my office is 39, 40, or 41, because the results are always coming back with that value. Or maybe there's somewhere between 37 and 42. By getting these values that are either really high or really low, it's telling me, wait, Gavin, there are pockets of people in your office that are either very old or very young. So you've got to be careful with how certain you make it seem with your answers. So what sampling variance is, it's the average squared deviation about the estimator's average value. Oh my gosh, Gavin is starting to talk gibberish to some of us. So the average squared deviation about the estimator's average value. What on earth does this mean? Let's have a look. So suppose we find that the average, we take a look at all these dots, we take an average of the dots, and we find that the value is 40. If I take a value, say someone comes back and they get the value 42, I then take a look at the squared deviation about the average value. So the average was 40. I take my 42 and I square it. I get the value. So 42 minus 40 is 2. 2 squared is 4. That's adding 4 to my variance. Suppose someone comes back with a value of 30. 30 minus 40 is minus 10. Minus 10 squared is 100. This is adding 100 to my estimate of the variance. But again, so it's 25 times more punitive to my measure of data quality, but this is making me happy because it's warning me. It's the canary in the coal mine. It's saying there is variability in your data. You have to be cognizant of this when you go to say that the average age at StatsCan is 40. Not everyone who works at StatsCan is 40. Tracy, I'm going to put you on the spot here. So can you turn your microphone on, please?
Yes, okay.
I'm going to give you an easy question first.
Okay.
What is age measured in?
Years.
Great. Age is measured in years. What is the variance of age measured in?
Years squared.
Great. That's the exact right answer. So as Tracy pointed out, these units are in years squared. Tracy, can you explain to those listening along what a squared year is?
It's a unit that you use to measure variance.
Yeah. So it's not a conceptual thing. It's not something we can, it's not tangible to us. So what on earth is a squared year? Thank you, Tracy. I'll let you off.
No problem.
What a squared year is, it's now in different units than our estimate. So our estimate here is in years, but our but the measure of variance is in squared years. So now they're not in the same units, and that's, I got to say for myself, that's kind of upsetting. They're not directly comparable anymore. So what we do is we take the standard error, which is just the square root. So we take the squaring away. So for the we find the sampling variance. It's a unit that we collect. I would say most methodologists, or 19 out of 20 or 99 out of 100, don't like working with variance. Variance is something that we calculate, but then we want to get it into a different measure. So standard error is a very common one. It's the square root of the variance. It's just to put it in the same unit. So it becomes much more comparable. When we talk about the difference between standard deviation and standard error is measuring the error of the estimate. Standard deviation is measuring the dispersion in the data. So one looks at the range in the data, or not the range. One looks at the distribution of the data. The other looks at the distribution of the estimates. All right, let's change this around a bit. So now what I've done is I'm changing this over to count. So I'm using the same sort of concept that I had in the second column, where I have all these little estimates, but now we've repeated this survey a lot of times. So I've sent everyone back out over and over and over again to repeat the same survey. These are the results they're getting. So someone managed to get 19 somehow. Again, I'm a little iffy on that result. Someone managed to get 65. Much more likely, we do have quite a few older staff working at StatsCan. But for the most of them, they appear in this middle. It's much more likely to get the value 40, 38, 42. It makes this bell shape, a bell curve. So by repeating this over and over again, we get this shape. So now what we're going to do is we're now going to talk about standard error and how this thing works to our advantage, or how we can use it. The way we're going to use it is we're going to start building confidence intervals, and confidence intervals are built using standard error. So it's 95% true. So there's a little squiggle on this because it's, I said it's between plus or minus 2 standard error. It's really plus or minus 1.96, but I can't be bothered when I make these graphs. So it's really plus or minus 1.96, but I'm going to say it's between 32 and 48. So what this means is when my students walk through the door after conducting their survey of 10, their interview with 10 people, I'll say to them, wait, before you tell me the answer, I bet your answer is between 32 and 48. And then they look down at their paper, and 95% of the time, 19 times out of 20, I'm getting it right. Because I've already seen the way the distribution works. After doing this hundreds of times, I've seen that 19 times out of 20, they're coming in this range. One time out of 40, it's going to be lower than 32. And one time out of 40, it's going to be greater than 48. And this is just a byproduct of the data coming in. So the average comes directly from the data, but so does the standard error. The standard error is just a measure of what we're seeing in the data. So my students come back and they say, Gavin, one, why are you sending us out if you already know the answer? But number two, they're saying an estimate of 32 to 48 is extremely boring. Anyone without conducting a survey could probably guess that at StatsCan, the average age is between 32 and 48. So I say, okay, look, I'm not a guy who likes to take a lot of risk. I'm a civil servant for a reason. I'm going to make it a bit riskier. And I say, okay, I say in my head, I'm 68% sure, but I tell them, okay, I think it's somewhere between 36 and 44. I'm only going to be right 68% of the time because that's what this normal curve is telling me. So as they're walking through, I'm going to say, okay, your answer is between 36 and 44. And 68% of the time, I'm going to be right. It's going to fall in this distribution. So what I can do is I can look in statistical textbooks, or I can use a computer, and I can say, okay, build me a confidence interval of a certain level of confidence, so 68 or 95, and it will expand or contract the size of the confidence interval around my average, so 40. So if I want to be really risky, I can make a very small confidence interval, but my percentage confidence is going to be very low. How certain am I that the answer is 40? I'm 0% certain that the average is 40. How certain am I that the average age is between 39 and 41? I can calculate this. How certain am I that the average age is between 32 and 48? I'm 95% confident. How certain am I that the age is between 36 and 44? I'm 68% confident. So I can calculate all these things out. That's what standard error is used for. That's what confidence intervals do. There's a fun joke that I like to share. Two statisticians are walking down the street, and there's someone walking the other direction, and the one statistician stops them, and they say, look, I'm sorry to do this, but can you pick a number between 1 and 1,000? Person thinks of a number between 1 and 1,000. The statistician goes, okay, your number was 728. The person goes, no, not even close, it's 430. And the person apologizes and they keep walking. The other statistician says to the first one, what on earth are you doing? He goes, one time out of 1,000, I look like a genius. Little joke there for you. All right, these confidence intervals. So these are what are critically important when we produce statistics. What is the range? How confident am I in my answers? We almost always do 95% confidence intervals. These are sort of the gold standard. You can do any one you want, but if you do 95% confidence intervals, you never have to justify it. If you use a confidence interval that isn't 95%, then you have to say the reason we're using a confidence interval that isn't 95% is whatever reason. So it's very rare that the general public will accept ranges on answers. The number one time they will do it, at least in Canada and probably in the United States, is when it's election time. People love confidence intervals at election time. So what we will see is, we will see something like, they'll do a poll weeks before the election. They will say party A is in the lead with 32%. Party B is at 29%, and party C is at, I don't know, 15%, and all these other parties add up to the rest. And so the supporters of party A that's at 32%, they're like, yes, we're winning. And the supporters of party B at 29% will be, okay, well, the margin of error on the survey is plus or minus 4%. So if I had 4% to 29, I get to 33. So there's a statistical chance we're in the lead here. And at least I do that. I'm sure other people do it as well. So we will see in the media quite often, according to a recent survey, in this example I've got here, 15% of Ottawa dwellings don't have a landline phone. The result is based on a sample of 1,234 dwellings, and is considered accurate within plus or minus 3 percentage points 19 times out of 20. So I believe that the true answer is somewhere between 12% and 18%, and I'm 95% certain that's true. If we conduct this survey over and over and over again, we're going to get it right 19 times out of 20. Okay. Confidence interval is what we can do all our cool party tricks with. Cool and party tricks is up to interpretation. I mean, amongst other statisticians at lunch functions, maybe. But everything we need is right here. If you pick up medical literature, if you pick up any kind of science literature, this is the way they talk. They all talk about confidence intervals. They all do significance testing based on these ranges. Does my range overlap, yes or no? And they'll look at different models. This is where it is. And so when I was in university, this might be true of you. This might be true of Tracy. Actually, Tracy, here, unmute yourself again, if you don't mind.
Sure.
So now we're going to look at coefficients of variation. Did you learn about this in university?
No, not at all.
So I have a slightly better education than Tracy, wink, wink. My professors used to teach us this, and I swear, in my mind, I'm not lying. This was 1 point on every exam. It was always a question of CVs. 99% of the exam was on stuff that was relevant, and one question for 1 point was always on coefficient of variation. All of the students always got 0 on it because they were like, what is this thing? Why do I need it? And as a mathematician, I still say this, why do I need this thing? So this is why I need it, and I'm going to talk about it for the next few minutes. So coefficients of variation is something that we produce for our statistics. So in my example with the age of people in Statistics Canada, I said my estimate has a standard error of 4. So as soon as I say standard error of 4, I can go plus or minus 2 to get 95%, and go plus or minus 1.68 to get, plus or minus 1 to get 68% confidence, and I can look up any number I want. I'm done. But this is the problem. The problem is that the standard error alone is insensitive to what the actual estimate is. So for example, Statistics Canada, the average age example, my 95% confidence level was 32 to 48. But let's look at another example with a confidence interval of 4, a standard error of 4, sorry. Let's look at metric tons of wheat produced in Canada in 2019. So there were 32,347,800 metric tons. A 95% confidence interval on this would be 32,347,792 to 808. I know for a fact that those last 2 digits on the metric tons are just rounded anyways, so this confidence interval doesn't make any sense. But we now see the problem with what happens if I have a standard error of 4 on a value of 40, and what happens if I have a standard error of 4 on a value of 32 million. Now, if I produce this statistic on metric tons of wheat produced in Canada, Tracy, today's hot seat for you. So the chief statistician sits on the 26th floor at Statistics Canada. If I produce this metric ton of wheat thing with an estimate, a standard error of 4, I'm going to get marched up to the 26th floor. And there's 2 potential reasons I'm getting marched up to the 26th floor. Tracy, you want to hazard a guess on either of them or both?
You're in trouble or you're in trouble.
Oh, one is I'm getting fired. One is I don't understand how statistics work. So you're right, I'm in trouble. But the other, Tracy, there's a positive side. Perhaps I'm some sort of demigod of statistics and I've managed to nail this estimate. Now, I've probably wasted a lot of time and resources to get it, so maybe I would be in trouble anyways, but it could be that I got this. But what it's definitely showing is I probably don't understand how standard errors work, because that second result is like, I mean, just by the fact I've rounded makes it impossible. So what we do is we want to make this, we want to create the statistic that's dependent on the estimate. So we create this thing called the coefficient of variation. And what we do is, this is, I think, this is the equation that I put in here is for CVs. So it's the standard error divided by the estimate and multiplied by 100%. So it becomes scale independent. If I say I have a standard error of 4, you have to ask me, how big is your estimate? If I say I have a CV of 10%, you no longer have to ask me how big my estimate is. You just know that I have this 10% error on it, the CV of 10%. So that's how this works. This is what makes CVs important. They're mostly, in my opinion, they're there to write policy. So for example, The guidelines for the Canadian Health Measures Survey, category 1, which is publishable if you have a CV between 0 and 16.5%, we publish it without any further sort of warning. 16.6 to 33.3 becomes restricted. So we would not publish this. We may not publish this number. What we would do is the users would have to then ask us, I see that you have a restricted estimate because the CV is too large. I would like to know what it is. And we say, okay, you understand that big CVs make for estimates that aren't necessarily good. And they go, yes. We say, okay, here it is. And in this case, if we have a CV that's above 33.3%, we just won't publish it because we don't have enough confidence in what that answer is. So in our in my Statistics Canada example, the CV was 10%. So it's 4, which is my standard error, divided by the estimate, which is 40, times this 100%. So it gets us 10%. The wheat example, my CV is like 0.00001%. It's fictitious, it's impossible. Again, I'm getting fired. So the CV allows policy writers to write, this is what we're going to do if your CV is a certain value. This is the level of confidence that our bureau wants when we publish statistics. It's much more for the bureaucrats to write policy. The mathematicians, the analysts and stuff don't use CVs. In fact, what they do is they reverse engineer CVs. If I see that there's a CV of 10% on an estimate of 40, in my mind, I will immediately say, okay, that means there's a standard error of 4%. So you can sort of like unlock the answer going the other direction. So that's sort of what this is for. Okay. So just as a conclusion, this is timed quite well, actually, considering the errors at the beginning. Measuring survey error serves its many purposes, right? So it's going to inform the users of the validity of the data we're producing. So whether it be the actual the non-sampling errors, which is the actual errors you made that you're telling your clients and your population about, it's good to tell them, we had the following mistakes. Anytime you're willing to admit to a mistake, people have to sort of applaud that, say, okay, good, they're willing to admit they've made mistakes. And when we talk about sampling error or sampling uncertainty, when I became chief statistician of the world, then that's telling them, okay, my point estimate is 40. I think the average age is 40. And you say, okay, well, how certain are you of that answer? Well, I'm pretty certain it's between 32 and 48. I'm 95% certain it's between 32 and 48. So that's why we measure the sampling error. So I open the floor to questions. I really hope this has given people who were uncomfortable with the idea of what these statistics were, an idea of this is how that they're used. Again, the only equation I put in this had to do with CVs, and CVs are the least used statistics of them all. So I really wanted this to be about understanding when they're used, how they happen. And so I hope this sort of gives people a better idea of it. So I open the floor to questions. And again, if you have sort of deeper questions than any ones that I may be able to answer right now, I invite you to email Tracy directly or this really long email address that we have for the Prask team.